Today I will going to talk about in-situ electric control of antiferromagnetic domains in an antiferromagnetic insulator, that is cobalt oxide. Okay, so before going to my results, details of my results, I would like to introduce the magnetoelectric effect, which is the main driving mechanism for the manipulation of antiferromagnetic domains in this present compound. So the magnetoelectric materials are those where, due to the absence of spatial inversion and time reversal symmetry, electric polarization can be induced by applying a magnetic field, and magnetization can be induced by applying an electric field. So this is the general expression of total energy of a material placed in a static electric and magnetic field. So in this expression, the dominant magnetoelectric coupling term is indicated by this one, alpha EH, where these other terms containing E and H are higher order magnetoelectric coupling. So from this expression, one can easily derive the expression of polarization and magnetization. So here you can see that in magnetoelectric material, by applying magnetic field, you can induce electric polarization, or by applying electric field, you can induce magnetization. Okay, so next I will talk about how we used this magnetoelectric coupling to manipulate antiferromagnetic domains. So the materials we are interested in is cobalt oxide. So this is a simple A-site magnetic spinel that has a cubic centrosymmetric structure at room temperature. So where the magnetic elements are cobalt 2+, which occupies tetrahedral sites and form a diamond lattice. On the other hand, the non-magnetic elements, cobalt 3+, they occupy octahedral sites and form a pyrochloride lattice. So this compound undergoes a simple collinear EG-axis type antiferromagnetic ordering below 30 Kelvin. So using neutron diffraction study on powder samples, it was proposed that the EG axis of this compound can be either along cubic edges or along cubic body diagonals. Interestingly, if you look at the magnetic point group of these two magnetic structure, you will notice that both of these two point groups allows linear magnetoelectric effect. Okay, so furthermore, if we consider Landau theory, and if we look at the expression of linear magnetoelectric interaction in this compound, you will get an expression like this, which contains terms in LMP. And from this magnetoelectric coupling, one can easily deduce the form of linear magnetoelectric matrix, which is given by this one, where you can see that only off-diagonal elements are non-zero in this orthogonal XYZ basis. So this particular form of magnetoelectric coefficient suggests two important points. So first one is, if you apply orthogonal electric and magnetic field, you can induce an electric polarization in this compound. And the second point is, the magnetoelectric effect in this material is fully governed by the orientation of antiferromagnetic nil vector. So that means if we probe magnetoelectric coefficient, basically we can probe the orientation of the antiferromagnetic nil vector in this compound. Okay, all right. So here in this slide, I have summarized the presence of linear magnetoelectric effect in this material, where both of these two panels showing temperature and magnetic field dependent polarization data were measured after cooling the sample with orthogonal electric and magnetic field, and this polarization was measured after removing electric field. So you can see that below nil temperature, electric polarization emerges, and it increases with increasing magnetic field. And we calculated the linear magnetoelectric coefficient, which reaches nearly 12 picosecond per meter. And this value is nearly 4 times higher than the well-known magnetoelectric material chromium oxide. And in this panel, I'm showing you how, depending on the sign of pulling electric and magnetic field, one can create two opposite antiferromagnetic domain states. So while we cool our sample with plus E and plus H, we found a linear pH curve that has a positive slope. So that means the linear magnetic coefficient is positive here. And since this curve is nearly linear in the whole magnetic field range, it suggests that we have a antiferromagnetic monotone state here. And let's assume that this antiferromagnetic monotone state is denoted by plus Ly. So if we cool our sample with minus C and minus H, we end up in the same antiferromagnetic monotone state. Interestingly, if you switch sign of any of these two fields, we end up in a linear pH curve, but with opposite slope. So that means we have minus Ly antiferromagnetic domain states in this case. So since by changing sign of either electric or magnetic field, we can change the antiferromagnetic domain states from plus Ly to minus Ly. So it suggests that these two domain states must be interlinked with each other with not only time reversal symmetry, but also with spatial inversion symmetry. So indeed, that is the case if you look closely in these two magnetic structure, where I just indicated these red dots as the inversion center of the paramagnetic cubic phase. Okay, so now the question is, can we switch between these two antiferromagnetic domain states in situ, isothermally within the magnetic order state? So for this, what we did, we directly cooled our sample to 4 Kelvin without any electric and magnetic field, and we measured polarization by varying magnetic field in the presence of an in-situ electric field. We find that due to negligibly small anisotropy energy, as indicated by this image data, we can create a plus Ly monodome state out of a virgin multi-domain state in situ. And most interestingly, if we reverse the magnetic field, we found that the slope of this pH curve is also reverses its sign. So that means we have a switching from plus Ly domain state to a minus Ly domain state at 4 Kelvin within the magnetic order state. Okay, so next we started this switching of antiferromagnetic domains by pulse electric field. So here we measured magnetic electric current by applying up, down voltage pulses. And this magnetic electric current exhibits sharp peaks whenever there is a change in magnetic electric polarization. So from this current data, we could calculate the electric field dependent magnetic electric coefficient, and you can see that it exhibits a typical hysteresis loop. So this hysteresis loop suggests that we have created an in-situ monodome state plus Ly, and also we could switch this antiferromagnetic monodome state in a non-volatile fashion. And furthermore, we perform this measurement by applying million times of pulses, up and down pulses, where we saw that the switching efficiency defined by delta alpha does not change at all after this repetitive switching. So next we calculated the switching time, which is an important parameter in antiferromagnetic spintronics. So in this panel, we are showing the dependence of switching time on the rise time of the pulses, where the rise times is defined by this horizontal bar here, and the switching time is defined by the full width at half maxima of these current peaks. So from this rising time dependence of switching time, we found that the switching occurs within few microseconds, and since this behavior is linear down to few microseconds, this result suggests that the intersecting switching time must be faster than the microseconds. So to achieve a faster switching speed, we used another second experimental scheme where we could apply voltage pulses down to nanoseconds, and we could measure the change in magnetic electric coefficient and also switching efficiency via pyroelectric current measurement before and after applying voltage pulses. So here we found that the switching, we found a partial switching when we reduce the pulse length till nanoseconds, 9 nanoseconds. However, if we apply these 9 nanosecond voltage pulses several times, we found that we could achieve 100% or complete switching efficiency. So these results are in line with Marx's law and suggest that the intrinsic switching time must be faster than 9 nanoseconds also. So next we studied the kinetics of the antiferromagnetic nil vector. So where we rotated the magnetic field in the XY plane in the presence of an electric field applied along the Z axis, and we measured polarization component PZ. So here we assume that during the course of rotation, the L vector remains in a plane perpendicular to the magnetic field always. Okay, so here this purple curve indicates our experimental polarization data. And to analyze this data, we used a model based on lambda theory, where we calculated the expression of polarization and total energy as a function of theta and phi, where these two angles denotes the orientation of magnetic field and antiferromagnetic Nil vector. So based on this analysis and based on our experimental data, we found that the antiferromagnetic Nil vector rotates smoothly within the XY plane. However, for certain angular range, the L vector rotates with preceding magnetic field, while in the other angular range, the L vector rotates with following the magnetic field. Okay, so this smooth rotation of antiferromagnetic Nil vector suggests that indeed we have a very weak anisotropy energy in our system. Okay, all right. So now this is all about my results. So I will summarize it. So in this talk, so I discussed the presence of linear magnetoelectric effect in single crystals of cobalt oxide for the first time. It's not reported yet. And then I demonstrated how we could use this linear magnetoelectric effect to switch antiferromagnetic Nil vector or to rotate this antiferromagnetic Nil vector in situ isothermally. And also we found that the interesting switching time of the antiferromagnetic domains must be faster than 9 nanoseconds. So with this, I would like to thank you all for your attention.
Thank you very much for this talk. I'd like to open the floor to some questions now. If you would like, we should have time for one quick question if someone would like to raise their hand. Okay, then maybe I can ask a quick question. Where do you see the future of this work going? What are your next steps?
Okay, so the thing is, currently in antiferromagnetic spintronics, so people are mostly working on antiferromagnetic metals, which are non-centrosymmetric metals, antiferromagnetic metals, but there the major challenge is Joule heating caused by the electric current. So in this direction, since these materials are insulator and you can tune or manipulate the antiferromagnetic order parameter by electric field, then you don't have to think about the problem associated with the Joule heating. So I guess in future there will be some new materials where you can easily manipulate by electric field by magnetic coupling.
That will be very interesting to see. Yes. Yeah, thank you so much.
Indeed. Thank you so much for it.